Okay. Okay, let's get started. Oh, I suppose today there will be a lot of students join, right? It's the final class. But anyway, our plan is as follows. So first we'll give a quick review. I'm not gonna touch the detailed content about the course because I will leave it as an exercise for you. But I will just talk about what kind of things you need to pay attention to. Like you can spend, I'll suggest to spend 2 or 3 days, go over all the slides, lecture slides, and also look at the written problems in the homework assignments. That should be sufficient. And you don't need to think about like, okay, you don't need to worry about like if there's some programming failing problem or ask you to write down a set of pseudocode because it's an online exam. So there won't be any those kind of will be what? Negative points. No, I've never I've never tried negative points before. That's kind of like crazy to me. Yeah, I know some kind of classes. I don't know, really. Do you know any class they have like negative points? Okay, yeah. Anyways, it's not my style. Okay. So first of all, oh, by the way, after the final review, we'll talk about some practical advice when you apply machine learning, and hopefully that will be benefit your practice of machine learning in the future. Okay, first, I want to highlight the schedule of the final exam will be next Thursday, December 15th, right? And the time is, this is scheduled by the university, it's not by me. There's some official website you can check. It's from 8 a.m. to 10 a.m. So be sure to get up early. But you don't need to worry about how to get to the classroom because we're doing it on Canvas. So we'll keep reminding you in the Canvas notice to ensure that you won't miss that, like due to all kinds of reasons. And if you look at Canvas, you will see that right now it's not published, released yet. But when you look at the quizzes section, at that time you'll see some final exam. You just click into that. You have 2 hours to finish. I guess 44 problems, 49 problems. I don't remember exactly, but basically it's like that. Okay. So here is the final exam policy. So first is the open book. Is open website. That means you can click into our course website and you can check the PowerPoint slides if you like. However, please do not search or post questions online. Like, do not ask questions in some QA website like Stack Overflow. That's not allowed. And most problems are just single multiple choices. Right. So we'll give you questions. We'll give you some items. You can select which one you do, which one is truth, which ones are true, and which ones are false. Right. And also there will be a few text description problem. So you don't need to worry about like math, right? You don't need to write down any math expressions in a text description box. So basically, they'll ask the problem will be like, okay, can you explain why like we encourage large margin during the training, right? What you need to is not to write down, okay, what's the definition of margin, how to compute distance, all kind of stuff. It's not. You just say, okay, maximizing margin is equivalent to reducing the VC dimension. Why? Because the visit dimension is determined by the margin as a so-called data-dependent visit dimension, right? And the generation error bound is determined not only by the training error, but also by some term determined by visit dimension. So just explain clearly this logic chain. Does it make sense? Right? So you don't need to write down formulas. But if you want to write down, it is okay. But it's not that is not a crucial part, right? We're just testing if you understand the ideas of those algorithms or ideas of those frameworks, like what's the difference between risk minimization, empirical risk minimization framework, and regularized risk minimization framework, right? Why do we need some regularization? Right? What's the connection between MLE and risk minimization principle and map estimation and the regularized risk minimization principle, right? So it's just test your understanding. So try to hit the point, right? Don't write like essay. It's not necessary, right? Don't write a very long article. It's not necessary. Just to hit the point, right? And also, to be fair, like the problems are kind of like randomly picked up from some kind of library. So, and also randomly permitted. That means you might deal with different orders of the problems. I mean, for different students. Right. Okay. Any question regarding this policy? No. There won't be any numerical calculation. Other question? So overall, it's pretty easy. It's much easier than the in-person exam we did before the COVID. So actually, in the past 2 years, I guess 2.5 years, we used this online Canvas. We feel like it's convenient for everyone. It's not, and also help relieve your stress, right? You don't need to really worry too much about that. But we do need to check if you really understand what we have discussed throughout the class, right? We don't want you to recite everything. That's really unnecessary. So that's why we allow like open book. But that doesn't mean like you can just do it without preparation. That's not a wise strategy. Okay. And coverage, the coverage will be spent the whole semester. Right? So we might ask you questions about decision trees, from decision trees to AdaBoost, from AdaBoost to perceptron, SVM, neural networks, backpropagation, logistic regression, those stuffs. Okay. So here is our suggestions. So review the lecture slides, make sure that you understand every slide we have discussed in the class, and carefully go through the paper problems in the homework assignments. You just look at the paper problems, and the final exam problems won't be harder than paper problems. Right? Not to mention that you're not required to calculate anything or derive anything or prove anything. Okay, any question regarding this schedule? Everyone's comfortable, right? Okay, so now let us just quickly go through. We want to make a thread that connect all what we have discussed throughout this semester, right? So throughout this semester, we're talking about machine learning, right? This is an entry-level machine learning class, right? So we first gave a kind of formal definition. What is machine learning? Right? And then we talked about a variety of learning models and algorithms. But I have to say that what we have touched is just a very small subset of learning algorithm models, because this is really a giant area. Like new models and algorithms are invented every minute, right? So we're not able to cover all of them, but we do pick up those classical representative ones which are widely used and which are very popular, also reflect important concepts and ideas, right? In the future, you might see new algorithms, new methods, but the design ideas are underlying ideas won't be too different from those existing methods. Okay. And also through the discussion about those different learning models and algorithms, we actually summarize the principles. We can get different learning principles, right? Like as we just mentioned, how do you compensate the loss? If you just focus on minimize the training error, it's called empirical risk minimization, right? And we found out it's not good because training error is good, does not mean like your generalization error is good, right? We really want to reduce our generalization error, right? So that then that leads to the generalization error bound in the computational learning theory framework, right? So we have some generalization error bound. That means the bound tells us, okay, we not only need to reduce the training error as much as possible, but we also need to control the model complexity, right? So that's why we need to add some regularizer. And then you need to know some kind of basic ideas about learning theory. So we don't cover much in the learning theory, right? We don't want to prove anything. However, we do want you to understand the basic concept, right? Like pack learnability, right? Why do people propose this concept called pack learnability, right? Probably approximately correct, right? That's because the data is random, right? You cannot assert that, okay, those algorithms will definitely give you 99% accuracy in the generalization sense, right? That's not possible because it is dependent on the data. That's why your conclusion has to be some kind of probabilistic conclusion. And good algorithms are those ones who are efficient and also can achieve good generation performance with large probability. And also, we talk about implementation and practice. So this class emphasizes a lot in practice. That's why some students may feel like stressful because you have to implement those algorithms from scratch. You cannot call some existing libraries. But we believe that only through some practicing, right, you will understand why the algorithms work, right? How it works and when it works, right? It will be very, very important if in the future you want to continue applying machine learning to address your own problems. So what is learning, right? So learning in essence is generalization, right? You are given some training examples, some label examples. Hopefully you can extract some nature of the target function underlying those training examples so that when you meet some new examples, you can generalize it, right? So the following definition is given by Tom Michel. Right. A computer program is set to learn from experience E. Here is E is really referred to as training data, right? With respect to some class of tasks and performance measure P, if its performance at tasks T as measured by P improves with experience E, right? It just tells you that, okay, if you add more and more training data, your learning algorithm can keep improving in performing that specific task, right? So actually this definition is formal, but reflects some kind of limitation. It actually differentiates the machine learning and the general artificial intelligence, right? So because all this definition is talking about, okay, how can we improve the capability in doing some specific task, right? However, in general machine learning, in general artificial intelligence, we're interested in that, okay, if you have some like a general machine that for any task, as long as you give some kind of experience, it can keep improving, right? This actually has a huge difference. So it sounds like, okay, I just remove the constraint of the like finite number of tasks. However, if you remove that constraint and then you want to push your algorithm to be able to learn and generalize to all kinds of tasks, that is really, really difficult, and which I think is the major bottleneck of the current machine learning and artificial intelligence. But anyway, this is not the scope of our class. Okay, so here's this paragraph. I really like this like this figure. It shows how our learning, machine learning, is conducted. Right? So to formulate the machine learning problem, we need to identify the instance space. Right? So what collection of examples you want to classify, you want to predict, right? And then you need to define label space. Label space actually reflects the task. Right? Suppose you want to do binary classification, then your label space is just binary, 1 minus 1. If you do a categorical prediction, like you have multi-classes, then your label space is discrete 1, 2, 3, 4, 5, right? This is very common. Like if you want to do the image classification, you know, okay, there are like thousands of possible types of objects, right? You have thousands of categories. And if you want to predict continuous values, you want to predict the stock price, you want to predict the temperature, precipitation, then it becomes a regression problem, right? So actually the instance space and the label space jointly define the specific task you want to use your machine learning method to address. Right? And then the basic assumption underlying this is that we assume, okay, there's a underlying target function, right? Which give any instance in the instance space, it can give you the correct label. And the goal of the learning is to find out this target function. And so we have like a different protocols for learning, right? For supervised learning, so we're gonna collect a set of instances and their ground truth labels, right? So this data will be fed into the learning algorithm, and the learning algorithm will find out a learned function G from their hypothesis space. Right? So our expectation is that G is at least very close to the target function F. Right? But based upon what kind of training data you will give the learning algorithm, it defines different types of learning method, right? So if you have if you don't have labels, right, you only have the instances, then this is called unsupervised learning, right? If you only have a portion of the examples have labels, and the other portion of the instances do not have labels, this is called semi-supervised learning. Right? We do not cover unsupervised learning and semi-supervised learning, but in the future, if you are interested in that, you can take a look. It is nothing different from the how we conduct supervised learning. Right? How do you construct laws? So the laws can encode both the supervised data and also unsupervised data or semi-supervised data. Okay, and based upon this framework, right? This is a supervised learning framework. We talked about a variety of learning models and algorithms underlying this framework, right? We talk about decision trees first, which is very intuitive and it's highly interpretable. It's very nice algorithm, it's very widely used. However, decision trees are not linear models. Right? Here, we just want to emphasize decision trees also looks really simple, but it can be quite nonlinear. Right? And then we talk about boosting ensemble learning. Basically, boosting ensemble methods try to combine a set of weak learners, right? So that we can derive a very powerful learner, right? A very commonly used weak learner is the decision stump, right? Only one level, right? And we talk about AdaBoost, the most classical boosting algorithm. We talk about random forest, right? So I'll explain why random forest works. But here, the random forest is not to combine weight classifiers. Right? Random forest is trying to combine like overcomplicated classifiers. Like you can train your decision tree to be like as deep as possible, as wide as possible. Right? But by combining them, as we discussed in class, there's a variance and bias trade-off, right? For overexpressive models, they have a smaller bias but large variance. Right? But your generalization error is determined by both bias and variance. Right? So the rationality of random forest and also general ensemble method is that, okay, if I do the average of a set of strong classifiers, it doesn't change the bias. Right? However, because you're doing error region, right, you're effectively reducing the variance. So overall, your generalization error will be will be reduced. Right? So just make sure that you are aware of this bias and variance trade-off is very, very important. And then we'll talk about linear regression, right? The first linear model we'll talk about. And we'll talk about least mean square method, right? We'll talk about the loss definition of that, and how do we minimize that with gradient descent framework and with stochastic gradient descent framework. Right? And then we talk about perceptron, support vector machines, and perceptron and support vector machines are both about linear classifiers. That means from the modern perspective, they are the same, right? And they use the same linear model for the classification, use same rule to do the classification, right? However, the training is totally different, right? For perceptron, it's this online training, it's a lazy training, right? So it just pass through those examples one by one, only when the example is misclassified by the current model to update. Otherwise, it doesn't update, right? And we talk about perceptron mistake bound theorem, right? We talk about when perceptron work and when it doesn't work, right? What if the data is not linearly separable, right? Perceptron will enter into a infinite loop, right? Cyclically goes through a set of distinct weight vectors, right? When the data is linearly separable, perceptron is guaranteed to converge. We have some beautiful bound about number of mistakes or number of updates when you run the perceptron algorithm. Right? And then we'll talk about support vector machines, right? So to prepare the support vector machines, we introduce the basic concepts of pack learnability, right? What is pack learnable? Pack learnability essentially is a way to differentiate efficient learning algorithm and inefficient learning algorithm. Right? So what is efficient learning algorithm? It says, okay, if you do not use so many examples, right? You use a polynomial number of examples to a bunch of parameters, and your computation complexity is also a polynomial complexity, then you can learn the family of target function, right? Under arbitrary like thresholding about generation error and confidence level with high probability, right? This is called pack learnability. Right? So although the definition is really tedious, it's lengthy, right? However, what you need to do is you need to capture why they're going to define pack learnability in that way. And then we talk about, okay, through some kind of tail bounds, right? We derive the generation error bound for the agnostic learning framework. You see that it's very beautiful. You have your generation error is upper bounded by the training error plus some term controlled by the model complexity, right? And then talk about how do we formalize or evaluate model complexity. Right? For finite hypothesis, then we just use logarithm of size of hypothesis space. However, for the infinite hypothesis spaces, like even linear classifiers, the hypothesis space is infinite. You can now use log size of hypothesis space as the measure of the complexity. That's why we introduced VC dimension, right? And it's based on the idea of the shattering, and the VC dimension is the effective measurement of the model complexity, right? And then we give the general results that support vector machine. The generation error bound is upper bounded by the two terms, right? So naturally, we want to minimize this bound, right? So that means we not only need to minimize the training error, we also need to minimize the VC dimension. Then there's a connection between the margin and the VC dimension, right? The connection is from the Vapnik theorem, right? We have given that, right? Margin actually reflects the VC dimension. The larger the margin, the smaller the VC dimension. That's why when we do the training of support vector machines, we encourage to maximize margin, right? And then there's a bunch of like formulation of support vector machines, right? We start from the primal form, then we move to the dual form, right? And primal form can be further, but by the way, please be clear about how we kind of simplify the SVM, right? The straightforward formulation of SVM is that, okay, I'm going to maximize margin, right? But the margin is the minimum distance between the data point and the classification boundary, right? So that's actually two-level optimization problem, which is really, really difficult to optimize. And then we use some kind of trick, right? Linear classifiers, their weights that are invariant if you just skew your weights by some positive factor, right? So we can we can put extra constraints that your function margin is simply 1, so that you really don't need to perform the inner minimization. Okay? So you don't need to recite details as I discuss this, because I've taught this class so many times. To me, it's really, yeah, it's really every details is just pop up in my mind. But just to give you a clue, right? To give you a lead, right? After that, you can review those details, right? So after we introduce these extra constraints that the function margin is 1, then we remove the inner minimization problem only to do the outer maximization problem, right? And then we convert this problem into a constraint optimization problem that will relieve the problem difficulty, right? And then we talk about the soft SVM, right? What if the data is not linear separable? Then we allow some data points to break into the margin, right? And also, we talk about in the primal form, right? How do we use the stochastic subgradient descent to train SVM? Right? Then we talk about dual form. Right? We spend quite a few features, talk about quite a few lectures to talk about dual form. Right? The reason we want to introduce dual form is that we want to introduce the so-called kernel method. Right? If you want to do some nonlinear transformation over the input vectors, so in a higher dimensional space, you train linear classifier. So we can still use all kinds of linear structure to train a nonlinear classifier. This is a very powerful method. That's called kernel method. Right? And when you transform SVM into its dual form, it is a lot easier to do this, because when you calculation, you need to just calculate the inner product between the test input and every training input, right? And now, if you want to do some nonlinear transformation, you just replace this inner product by the kernel function, and that's it. That's why in our SVM homework assignments, the implementation is really easy, right? Just a few lines of code. Right? However, you do need to know how we arrive at that line, that a few lines of code. Right? And we'll talk about kernel SVM and kernel perceptron, which is your homework. Right? And finally, we'll talk about artificial neural networks. Right? The definition of artificial neural networks is really straightforward. You just concatenate a bunch of building blocks, right? Each building block is a linear transformation and nonlinear activation function. Right? You just concatenate them together. You make it in this way. You composite a very complicated network, right? And the major bottleneck of neural network is the training procedure. Right? Even you use the stochastic gradient descent, right? You imagine you have like hundreds of thousands or even millions of parameters. Right? The gradient calculation is very, very costly. That's why we introduce backpropagation. Right? Backpropagation essentially is a very smart way of chain rule. Right? So starting from the top layer, the upper layer, right? You just calculate and catch the partial gradient of the loss with respect to every neurons in the current layer, right? Then you leverage this results to calculate the partial derivative with respect to every neuron in the next layer. So you don't need to duplicate or repeat the computation. Every time we move to one layer to another layer, what you need to do is just something you have to do, right? Is something never computed for things that have been computed. You never need to repeat it, right? That's the idea of the backpropagation. Right? It's quite mechanical and tedious, but that's very, very appropriate for algorithms. And then we talk about logistic regression and IUBAS, which is actually a Bayesian learning framework. Right? We talk about what is the notion of Bayesian learning, right? And we talk about the first notion is to learn a probabilistic concept, right? We're going to predict the probability that your label is 1, rather than just tell the label is 1 or -1. Right? And IUBAS is another instance of machine learning, Bayesian learning, where we use probabilistic criterion to search over the hypothesis space. Okay, that's basically give a quick summary of what we have discussed throughout this semester. Of course, this won't be detailed enough, but hopefully this will be a useful lead for you to guide you through those lecture slides. Right? And from if we take different aspects of the view of those learning models, right? We can categorize those machine learning models as like linear models and nonlinear models, right? So linear models include least mean square method, that's for regression, perceptron, SVM, logistic regression, right? Because they have some linear structure in the model, right? And then we'll talk about nonlinear models. Right? So actually, we can roughly have two types of nonlinear models. One is that, okay, we're based upon like linear models, right? We want to preserve the linear structure on all the computational benefit, but we just do some feature mapping on that. Then this type of methods is really called kernel methods. Another type of method is that, okay, I'm going to construct a nonlinear models from scratch. Right? Like typical examples are neural networks, decision trees, AdaBoost, and random forest. So basically, I mean, even in the current cutting edge research of machine learning, like linear and nonlinear models. If you do nonlinear models, they're just roughly these two types of methods, kernel methods and other methods. And if we view how we formulate those models, right, we can consider those models as probabilistic models or non-probabilistic models. Of course, we spend most of time in talking about non-probabilistic models, right? But probabilistic learning is actually also a very wide area. We only introduced logistic regression and EBS as these two instances. For non-probabilistic models like neural networks, decision trees, SVM, perceptron, all kinds of stuff. But I will tell you that all those non-probabilistic models have their probabilistic version. Like for neural networks, we have Bayesian neural networks. And for decision trees, we have Bayesian decision trees. And for SVM, we have Bayesian SVM. For perceptron, we have Bayesian perceptron. You always have a way to assign some probabilistic meaning over the parameters of those models and do the probabilistic search over the hypothesis space. Okay. And there are a variety of basic concepts in the theoretical aspect, as we mentioned. This is not a theoretical course, right? We introduced theory. We just introduced the necessary concepts like PAC learning framework, right? What is PAC learnability, right? So what is sample complexity bound? What is the generation error bound? Right? So actually those bounds is derived by like very basic tools. Right? Mainly is the probability inequalities and tail bounds. Right? However, the results reflect like surprisingly amazing structure and insight. Right? And what is VC dimension? This dimension is used to measure the complexity of the hypothesis space. Like even your hypothesis space is infinite, it can often provide some finite measurement, right? So we can compare the expressivity of different hypothesis spaces by using their VC dimension, right? And how is the large margin principle derived by the generation error bound? This is what we have discussed a few minutes ago. Right? Again, there's no need to memorize them, but you need to really understand it. And also principle to train learning models, right? We actually talk about those following principles like empirical risk minimization, which essentially is to minimize the training error, right? However, if you only minimize training error, it can lead to overfitting. It won't necessarily give you a good generalization error. That's why we in practice, a better choice will be regularized empirical risk minimization. That is, in the last term, you add additional regularizer to penalize overcomplicated models, right? And also talk about probabilistic learning principles, right? Map estimation and maximum likelihood estimation, right? We have like very interesting connection to these two principles, right? As we discussed, right? If you're doing maximum A posterior estimation, if you take logarithm and if you just simplify the terms, and finally it will correspond to the regularized risk minimization. The essential reason is that the prior actually has a correspondence to the regularization. And if you're just doing maximum likelihood estimation, that means you don't have a prior, or your prior just uniform, it's uninformative. And then map estimation, maximum likelihood estimation really corresponds to the empirical risk minimization. And the learning algorithm gradient descent, stochastic gradient descent, and what are the advantages and disadvantages of gradient descent, stochastic gradient descent. We have discussed about this a lot, right? In practice, how to select hyperparameters. Right? So can we directly optimize hyperparameters in the loss? Okay. We use SVM as an example to show that, right? If you directly optimize the trade-off between the W transpose W and hinge loss, it will simply give you 0 C, right? That won't be reasonable, right? So the often used approach is to either use a holdout data set, right? You hold out separate data set, you just test what's the performance of each choice of hyperparameter on this holdout data set, or you can use cross-validation. Right? So basically, those are all use some approximation to the generalization performance to guide the selection of hyperparameters. Everyone is comfortable, right? Okay. So finally, just to go review suggestions, I want to emphasize again, please go through all the lecture slides, understand the details, right? Go through the homework problems you have worked, but you don't need to you don't need to go through the programming problems. Okay. Good luck for the final exam. Okay, the remaining the remaining part is that I want to share some practical advice for building machine learning applications. I think that will be more useful if you want to continue to explore machine learning in the future. Okay? So we're going to talk about how to diagnose the problem of your learning problems. We're not talking about debugging because our TM has shared some debugging ideas or tricks before, right? We're talking about how do you diagnose problems. Suppose your implementation is correct. However, there's still all kinds of problems. How can we address them, right? And we're talking about error analysis. Right? Error analysis means that, okay, if you integrate many machine learning components all together to have a system, right? And they want to find out what is the bottleneck of the system, which component leads to the problem, right? And then we'll talk about how to develop machine learning algorithms or methods for a particular task. Right? We'll talk about two modes, right? Two working modes. Right? Research mode takes more time, is more refined, is good, but it's not very useful in practice. For example, if you're doing work in some company, they want with you for like 3 months to collect data, right? They want you to build up a prototype very quickly and do this fast iterations. Okay, first, how to diagnose your learning algorithm. So suppose you have to train an SVM or a logistic regression classifier for some task like spam detection. Right? You obviously follow the best practices for finding hyperparameters, like you use cross-validation, and your implementation is correct, for sure, right? But your classifier is only 75% accuracy. Now the question is, what can you do to improve it? So there could be a lot of strategies, right? There could be quite a few different reasons that cause the low accuracy or unsatisfactory accuracy. So let us first consider like different ways to improve your model. Okay? You might consider add more training data, right? Or you might consider change the features, right? You can either use more features, use fewer features, or even use other features, new features. Right? Or you can try to improve the performance by doing a better training procedure, right? You might consider like run your optimization for more iterations. You might consider use a different optimization algorithm, even change classifiers, or add some regularizers. So basically, there seems too many ways that can be used to try to improve your model. Of course, we cannot like do some kind of combinatorial attempts, right? Because there are too many ways, right? And also it depends a lot, right? So we want to make this process more systematic. How can we do that? First, we need to summarize what kind of problems can lead to the unsatisfactory performance of your learning algorithm. So basically, there are 4 common problems. Right? There might be a few more, but that will depend on your particular problem or particular application. Here we just summarize 4 common problems that could possibly lead to inferior accuracy or unsatisfactory performance of your machine learning algorithm. Right? What are the 4 problems? First, the data, your model might overfit data, right? You got very good training accuracy, but perform badly in the test, right? Second, your model might be too simple. It's underfit data. Like this target function might be highly nonlinear, but you just use linear regression. That's not powerful enough to attain good performance, right? And third one is your learning algorithm itself has a problem, right? Maybe your learning doesn't converge, right? You just stop too early, or you might stop too late. That's the algorithm perspective, right? And finally, it might be just because you use the wrong measurement. So this one actually is more often in practice, because in practice, your performance measure is not always based upon like test accuracy, mean square error, those kind of stuff. Okay? And actually, you have to like integrate with some domain knowledge and application specific things. For example, when I was a PhD student, right, I did an internship in Yahoo Labs. Right? They're doing a majority of their profit comes from like online advertising. Right? If you do online advertising, it's not like you just predict the accuracy of the clicks. Right? You're showing some ads on the web page. You just predict whether the user is gonna click that advertisement or not. Right? So it's a click-through prediction, but click-through prediction accuracy cannot comprehensively reflect the performance of your online system. Right? You need to come out like more complex measurement. Sometimes you don't. If you choose the wrong measurement, it actually does not reflect the actual performance of your learning algorithm. Right? And unfortunately, in many tasks, like in many applications, you have to come out some appropriate measure by yourself. That's like when I joined their group meetings, you have to report, okay, this is my algorithm, this is my measurement, and why my measurement is reasonable and can reflect the company's expectation. Right? And you need to justify this, and then when this is get agreed, right, then you can test on that. So this is actually quite important in practice. Okay, so now let us look at those problems one by one, right? And we need to first debug or decide if the problem of our model is one of those 4, right? How can we verify this, right? So let's look at overfitting, underfitting issue, right? So for the overfitting, so the basis says, okay, we got high training accuracy, but test accuracy is much lower, right? So the training accuracy is much higher than test accuracy, right? So that means the model explains the training set very well, but poor in the generalization, right? And on contrary, if your model underfits, that means your model is too simple. It even cannot well fit the training data, not to mention in the generalization step. Right? So that means, okay, both accuracies are unacceptably low. Right? The model cannot well represent the concept. how do we detect, right, if your model is overfitting or underfitting? Of course, you can use just final accuracy of doing this, right? You can just train a model. You believe the training is finished. Okay, you look at training accuracy and look at test accuracy, or you just look at and then you can determine, right? Another common used approach is to look at the learning curves. Okay? So we can gradually increase the size of training data. Okay? And this is where the training error varies. Right? At the same time, we want to look at how the generalization error varies. So, of course, it is reasonable to believe that, okay, as you add more and more training data, your generalization error keep decreasing, right? But then we can look at the gap between the training error and generalization error. Right? If the generalization error is significantly large than the training error, then what's the problem? Overfitting, right? So that means, okay, you're performing good for the training, right? However, for the generation, it is much worse. So by looking at this learning curve, it is easy to see that, right? Then what if the training and generation error is very close, okay? And both at a high level? Underfitting, right? So underfitting means that, okay, your model is too simple, right? It cannot capture the underlying concept, underlying ground truth, right? So that means it can even not perform well on the training data. And as a result, both training and generalization or test won't be good, right? Okay, once we have identified a problem, either overfitting or underfitting, right? We can look at those strategies we have just discussed and find out which ways can be used to address that problem, right? So if you use more training data, obviously it can help with overfitting, right? With more and more training data incorporate, it can make if your model is over complex, right? If it's too complex, like 100 layer neural networks, of course you need more and more training data to alleviate overfitting problem, right? And another commonly used strategy is to add regularization or play with regularization strengths, right? Because the regularization itself helps to penalize overcomplicated models. And from the feature perspective, like feature engineering, if we use more features, what's the possible effect? What's the possible benefit? It can help with underfitting, right? You can imagine, like, okay, previously my model is too simple, I only use 10 features. Now I add more and more features, actually increase the complexity of the model, right? If those features are kind of like capture the key characteristics of the target function, that would be a lot of helpful, right? So that's why use more features usually help with underfitting, right? However, if you use fewer features, you kind of reduce the instance space. It usually help with overfitting. That's why feature selection is very important in practice. If you use 1 million features, you might see overfitting, severe overfitting. But at that time, you can try to reduce a lot of like irrelevant features. Right? And how about use other features? It's hard to see, right? It could help with underfitting. It might also help with overfitting, right? You can remove some noisy features, incorrect features. Those features could mislead the learning of complex models, right? Because complex models trying to fit all kinds of data, right? No matter you're wrong or correct, right? So it can help with overfitting, right? But it can also help with underfitting, right? Okay, so now we discuss about how to diagnose overfitting, underfitting problem. We have pointed out a set of different methods to address those two problems, right? And now next, let us talk about how to diagnose the third problem, right? How do we make sure that, okay, it is your learning procedure problem, right? Your learning algorithm might not properly run, right? First, what if your learning does not converge, right? And as we discussed in the class, right, SGD, stochastic gradient descent, is the most popular method in practice. It is good, but it's also bad. Good means that, okay, you can use very small cost to update the model, very, very frequent. Okay? But the problem is that because you're doing stochastic gradient descent, you don't know when it converges. All the theory tells you that, okay, at the limit, when you run like infinite number of steps, it converges with probability 1, right? That's just to wait for practice, right? I don't know. I cannot wait for infinity time for it to converge, right? In practice, you have to stop at some time. Then the problem is that, okay, when do you need to decide to stop? A commonly used strategy is to look at the learning curve, right? You can look at how the objective of the training objective varies along the number of iterations, and look at the shape of curve. Right? If the curve, if currently you're at here, of course, it's not converged, right? And then, but at a later stage, we'll see that, okay, the curve of the objective looks kind of like stable. Then it shows convergence. However, I would emphasize this is just a very, very empirical check, because it might not be truly converged. Right? It's just showing, okay, stable. It might just still decreases very, very slowly. We don't know that. And unfortunately, in practice, we won't have like a very rigorous way to test that. You have to rely on your observation on that. Right? And usually, if after this point, right, even the function still keeps decreasing, right, objective still keeps decreasing. If it is too slow, then it might not worth us to keep running that. And that's the rationale. Like we should from the learning curve to pick up some point to stop. Does it make sense? Right? And of course, in this case, right, even at this stage, right, even it's very later stage, if you still see some trend of slowing down, it's better to stay and wait. But sometimes, if you look at very bizarre learning behavior, like the objective function perturbating wildly, and most likely it is the bug of your implementation, right? Or some wrong choice of the step size. Otherwise, you should see a general trend of decreasing trend of your learning curve. Right? Oh, by the way, I want to mention that those curves are quite smooth, right? This is not stochastic gradient descent. If you look at stochastic gradient descent, the curve typically is like this. You have some like perturbation for sure because you're doing stochastic gradient descent. But generally, you can still say an obvious trend of decreasing. Right? If you see like very wild perturbation like this, it's very likely that you have wrong implementation or you have a wrong setup of the step size. Right? I think everyone has tried this in your implementation of SVM or neural networks, right? It's very useful method. So now let us go back to look at those strategies, right? The list of strategies to improve our model, right? So we can see that to improve the training procedure, right? You can run for more iterations to wait until your learning really truly converges or close to convergence, right? Or you can use a more efficient learning algorithm. So both methods can be used to track the to address the problem that your learning algorithm does not behave well, right? Okay, this is the third problem, right? And then we talk about the fourth problem. Right? Are you marrying the right thing? This is something you should think about at the beginning of your right? Before you want to deploy or design any machine learning algorithm, you need to think about, okay, how should I measure the performance? If it's just like area under curve or accuracy or mean square error, that's fine. That is relatively easy. Right? But for other more complex problems, this one needs to be carefully designed at the beginning. Right? Otherwise, you'll get misleading result. Right? So, what to measure, right? Accuracy of the prediction, obviously, is the most common measure, right? However, if your data is unbalanced, then accuracy may be misleading too, right? Consider that your data contains like 1,000 positive examples, 1 negative examples. Okay? You can just build up a simple classifier where for every possible example, my prediction is just positive. Then your test accuracy is still 99.9 accuracy. And this doesn't make any sense, right? So this is not the toy example. Actually, it's very important for like disease prediction, like for example, some kind of rare disease. It only the chance that happens just to take like 0.1% of population. You want to build a classifier to predict according to some lab test, right? You want to predict if this person has this disease or not, right? If you just build up a blind classifier, like I just test, okay, this person is positive. Right? If you look at accuracy, okay, it's still very high because it's rare disease. It's just a rare disease. But of course, such kind of metric is not acceptable. So for this particular case, like if I'm unbalanced labels, right? A more commonly used approach is called F measure, right? So we're going to compute the precision and the recall. Right? Precision means that, okay, for all the examples, you predict, for all the positive predictions, you look at how many are correctly predicted, and the calculate ratio is precision. However, you also want to look at recall. Right? And among all positive examples, right? Like suppose you got 50 positive examples. However, you only successfully predict 40 of them. Then the recall is 40 or 50. Okay. But you totally predict, say, also 50 positive examples. Only 40 are positive. Then your ratio, then the precision is 40 or 50 as well. So there's a little bit difference between the precision and the recall. And then the F measure is just the harmonic mean or harmonic average of the precision and recall. Right? So I'm not gonna talk about details about this, but just to showcase an example that it's not always the case that, okay, you just use accuracy as a good measure. Like even for the simple case where your data set is unbalanced, then accuracy won't be a good measure anymore. Okay, you need to come out other measures. Okay, any questions so far? Okay, next, let us talk about the error analysis, right? So error analysis means that you're not dealing with a single piece of machine learning code. When you, in practice, how do you apply machine learning, right? This is where your machine learning stays, right? So this is really embedding the large giant system, right? For example, online advertising system, or text processing system, or autonomous driving system, right? You have some like very critical component for the machine learning, right? But you also have many other components, like, for example, this comes from some I think it's some text mining system, right? You have some configuration system, like to configure some settings, right? You have data collection step, you have feature extraction step, right? You have data verification step, like maybe deal with like missing data or privacy issue, right? After that, they feed the data into the machine learning model. The outcome will be fed into analysis tool, fed into the process management tools, and also you have to handle a huge amount of data, right? You have some like a computational infrastructure to support that. So I also need to talk about machine. You have to deal with machine resource management and service infrastructure, and all kinds of stuff. Right? This is very complicated. In general, machine learning plays a small role in larger applications. Before you apply machine learning, you often need to go through several steps like pre-processing, right? Like feature extraction and data transformations, all kinds of stuff, right? Then the natural question will be, okay, how much do each of these those components contribute to the final error, right? To improve the whole system performance, we usually need to conduct some kind of error analysis to explain what is the bottleneck, where is the bottleneck, and how should we improve. So here we give one example, like a typical text processing pipeline. Right? So here's the text, right? Some paragraph, some articles, right? Crawled by your crawler. And then you need to first partition them into the words, right? You do the part of speech tagging, right? And then you do some semantic analysis, usually some parsing tree, right? You do the tree parsing, you got semantic trees. And finally, you collect all the information from words level, from parse speech level, from the semantic level. You feed them into some machine learning based on application like a deep neural network, a transformer, and so on, right? You give some result, right? And also, each of those components, right? Although they all serve the final machine learning application, right? Each component can be machine learning driven as well. So that means they could be prone to errors as well, right? Then a natural question would be, okay, how much do each of those components contribute to the error of the final application? Right? How can we examine that? A common use strategy or efficient strategy is to do a step by step. How can we do that? Like we can try to replace each component by the ground truth and say how the final performance or final accuracy varies. Right? Here is the example, right? So if we just test the original system, right? We do this end-to-end prediction, our accuracy is very low, right? It's just 55%. Right? Now I want to look at, okay, if I replace each component, can I have a large increase of the final prediction error, right? First, we replace this words component, like with ground truth words, right? We do not do, say, we do total stemming, those kind of stuff, right? Then we found out, okay, the accuracy increases to the final accuracy of this system, right? Increases 60%, right? So that doesn't give you a big increase, right? And next, we replace the parse speech prediction by the ground truth parse speech. Then we found the accuracy increases to 84% accuracy. Right? This is a huge increase, right? And further, we replace the ground truth parse trees. We replace the parse tree results by the ground truth parse trees. Right? We found it further improves. It got 89% accuracy. And finally, if we replace every component as the ground truth, our final accuracy is just 100. So now from those accuracy changes, what can we conclude? which component should we improve? Power speech, right? Obviously, right? Why? Because once we replace it with some ground truth parts of speech, the performance improves dramatically. That means this component is the bottleneck of the whole system, right? However, if you replace other components with some ground truth, the improvement is reasonable, but it's not giant, right? So that means, okay, the most important thing to improve our system is to improve this particular component. Right? That's a common strategy, right? In general, we call it the ablation study, right? Suppose you have a large number of features, right? You want to know which features are good, which features are not good, right? So that you want to remove the bad features, you just want to preserve the good features to improve performance, right? How can we do that, right? You can just do this progressively, right? You first use all of features all together to make prediction. Then you gradually remove each feature and to see how the performance will change, right? For some feature, if you remove it, you might even get increase of performance. That means, okay, this feature is bad, right? For some feature, if you remove it, okay, you have a significant drop of performance. That means, okay, this feature is important, you should preserve. Okay, this is about error analysis. Any questions so far? Okay, and finally, we want to talk about some kind of useful practical experience, like how do you inject machine learning to your own task, right? Suppose you're working on some company, your boss is gives you some task. They want you to develop some classifier to predict or classify fish, right? So this is not a toy problem. I think 2 years ago, I taught this class, and one student came to me that he is working on some company in Salt Lake City. They asked him to develop a classifier about mosquitoes, right? Because for different mosquitoes, they're going to use different, I guess, different poison things to kill them or something like that, right? So that's very important. And he used some like recurrent neural networks and something doing this is working really well, right? So the problem is that, okay, suppose you're given this task, right? How do you plan to develop such a fish classifier? The first approach is called slow approach or academic approach, right? You carefully identify features, you get the best data, you design a software architecture. Maybe you design a new learning algorithm, completely new, right? And then you implement and hope it works. Right? So the advantage is that this method is very systematic. It might lead to a better approach, right? Might even be a new learning algorithm. So it's more research. It's more like doing research. To me, it's exciting, right? But in practice, it's not recommended, right? In practice, if you're doing things in this way, you're likely to be fired, right? Because your boss really wants to know, okay, do you get something in hand, right? Do you get something to test? And if it is working, then we can just deploy them in the production line. That's it, right? So in practice, we usually use the so-called hackers approach, right? You first implement something. You first from some off-the-shelf library, off-the-shelf model, you just try it and then give some performance and look at if it is reasonable or if it is satisfactory, right? If it is satisfactory, then your boss say, okay, that's good. Right? Let's turn to another project. That's done. Right? If it is not satisfactory, then you kind of diagnose what happens, right? You use all the things we have discussed to think about where's the problem, right? It might be features not effective, you need to add more features, might be like a model is not expressive enough, or it's too expressive, right? Overfitting, underfitting, all kind of stuff, right? And then you use those diagnose technique to iteratively improve your model so that people and your team, your boss will see, okay, you're keep progressing, keeping progressing. And also they always see you have something on hand that can be used or tested. Right? So this is in practice how people do things. Right? It's not only in some company in Salt Lake City. If you're doing things like working in Facebook, in Microsoft, in Google, they're always doing things like that. Right? Yeah, I got some student intern on Meta Fair research. It's about artificial intelligence. It's a very well-known research department, and he expressed his interest. He has a lot of ideas of doing those kind of stuff for the recommendation system. They said that they're very interested, but don't have time to do that. What they want is, okay, you just grab some kind of like tensor decomposition idea or library, just deploy it and test and see if there's performance improvement. If it is, then they just open a champagne, right? They don't give you they don't give you the time to design some completely new approach. Okay, so also when you deploy your method, right? We inject your machine learning into your own task, right? You also have to define the right evaluation metric, right? This is important, as we mentioned at the beginning, right? And also you need to design a loss function to reflect your evaluation metric, right? Otherwise, you might mislead learning procedure, right? You don't drive the learning toward the direction you want. And another important thing is that you should be extremely careful about the contamination, meaning that don't mix training and test data. Right? This is very common mistake. Even like highly experienced engineers might make some kind of mistakes. Right? So if you say your test performance is surprisingly good, right? Don't celebrate. First check if you happen to mix the test data and the training data. And also there are a bunch of other things you should pay attention to, like be aware of bias and variance trade-off. That's basically saying you need to choose the appropriate complexity of your model. Right? Like if you use neural network, you need to decide you are using 100 layers or just 2 layers. Right? And also be careful that your intuitions may not work in high dimensions. In practice, your data is often high dimensional, like images, they're always high dimensional. So, so don't trust too much about your intuitions, right? Because there's no proof by the picture, and also there are some curse of dimensionality, which that your intuition does not apply. Right? And third one is that don't misbelieve the theories. So a lot of theories, they look beautiful, they look elegant, but when you look at their preconditions, you may introduce a lot of unrealistic preconditions. If you do not, if you're not aware of those preconditions, then the theoretical conclusions are not correct. Right? They won't give you the guarantees they claim. Right? So that's why in practice, right, people always pay more attention on the final performance rather than, okay, if there's some theory which can support your model design. And also big data is good, but big data is not sufficient because big data is often noisy and often contains more mistakes. So data cleaning is very, very important. Although it sounds tedious, but it's very, very important. Right? And also your design of learning models, right, requires some knowledge to guide learner, right? That's why the domain knowledge is also important. Machine learning is not a magic wand, right? Or knowledge, right? Which model is the right one for this task, right? So people know that for some medical applications, decision trees or random forest might be the good choice. You don't need to use neural networks, right? But for computer vision tasks, you have to use neural networks because neural networks is the state of art. Right? It's much better than SVM or other methods, right? And you need to choose which learning algorithm, right? And you need to look at if the data violates any crucial assumptions that were used to define the learning algorithm to model. Doesn't matter, right? And the feature engineering is also crucial, right? So again, it sounds tedious, but in practice, it is important, right? There are some other miscellaneous advice, right? So first, don't try to build a very complicated models from the beginning. Right? Try simpler models first. For example, you can just try linear models or SVM. And if it works, then that's it. Otherwise, it gives you a way to debug or diagnose what is the problem. And in general, ensembles seem to work better. Right? You have a collection of models, and you train them individually, and you ensemble them, say, take an average. It usually work better. Right? And finally, you should be aware that some problem might not be learnable. And then, in that case, if you apply machine learning, that's not a good choice. Okay, that's it. And thanks for joining our class this semester. I know everyone like making a lot of efforts in doing this. This course is challenging, but thanks for efforts, and I wish all of you a great success in the future. Okay, and hopefully we can meet with each other like in my class in the spring or in other classes. Okay, let's stop here. No, it's not always bad. Sometimes even if you combine a set of highly correlated features, it can still give you better performance. Because you can imagine that unless these features are completely the same, even they're highly correlated, if you add them, you put them all together, it can give you more information than use just one single feature, right? It's not bad to incorporate highly correlated features.